This is a video on joint density functions. The question states, show that the following is a joint density function, and then find the probability that x is between 0 and 1, and y is between 0 and 2. And we're given the function f of xy is equal to 1/16 xy for x between 0 and 2, and y between 0 and 4, and the function is 0 elsewhere. Let's recall that a function is a joint density function if the function is always greater than or equal to 0 for all x and y, and if the double integral over the entire xy plane of the function is equal to 1. So first, this function is greater than or equal to 0 because it's 1/16 xy between 0 and 2 for x and 0 and 4 for y. So if x and y are both positive here, then so is 1/16 xy. And outside this area, the function is 0, which is also not negative. So secondly, I need to find that the double integral over the entire xy plane is equal to 1. So I take the double integral from negative infinity to infinity for x and negative infinity to infinity for y of f of xy dy dx, and I need to show that that's equal to 1. That's pretty much saying that if we throw a dart at the wall and we know we hit the wall, then the probability of hitting somewhere on the wall is 100%. That's why this double integral must be equal to 1. So let's take the double integral. Since the function is 0 outside of x between 0 and 2 and y between 0 and 4, I don't have to worry about that outside bounds because those are just 0 and they won't contribute to the double integral. So instead, I just take the integral from 0 to 2 for x and 0 to 4 for y of 1/16 xy dy dx. The integral of 1/16 xy dy is equal to 1/32 xy squared. And we're going from 0 to 4 for y. And if I plug in 4, I get 4 squared is 16. The 16 over 32 is a half. So I just get 1/2 times the integral from 0 to 2 of x dx. The integral of x is x squared over 2. The over 2 and the 1/2 become a 1/4, and I have x squared from 0 to 2. And if I plug in 2, 2 squared is 4. 4 times the 4th is 1. And note that when I plug in 0, that just zeroes out. So I really do get that this double integral is equal to 1. So I can conclude that this function, f of xy, is a joint density function. So now I need to find the probability that x is between 0 and 1 and y is between 0 and 2. So I take the double integral for x between 0 and 1 and y between 0 and 2 of the function. Notice that in this region for x between 0 and 1 and y between 0 and 2, we're up here, x is between 0 and 2 and y is between 0 and 4. We're not in the elsewhere part. So that means I integrate from 0 to 1 and 0 to 2 of 1/16 xy dy dx. And as before, the integral of 1/16 xy dy is 1/32 xy squared, and I'm going from 0 to 2. If I plug in 2, y squared, or 2 squared, is 4. 4 over 32 is an 1/8, so I'm left with an 1/8 times the integral from 0 to 1 of x dx. And then I integrate x dx, that's x squared over 2. The over 2 and the 1/8 combine as a 1/16 times x squared, and we're going from 0 to 1. So if I plug in 1, 1 squared is 1, and if I plug in 0, 0 squared is 0, so 1 minus 0 is 1, and 1/16 times 1 is 1/16. So I can conclude that the probability that x is between 0 and 1 and y is between 0 and 2 is equal to 1/16. And I'm done with the problem.